Hello, everybody. This is looking at chapter 10, specifically 10.1. And inside of this chapter, we're going to be looking at two samples now and determining if we have enough data to reject that null hypothesis. So whenever we're looking at two samples, we're going to be able to do some calculations. We'll be able to calculate averages, proportions, or we'll have something called a matched or paired sample, which we'll get to at the end of this chapter. The average is going to be what we're looking at today. And we're specifically on this lesson going to be looking at two independent samples from two distinct populations where we have an unknown population standard deviation. Sometimes they'll give us that population standard deviation, sometimes they will not. And if the sample sizes are small, we need the distributions to be normal. So you could go into Google Sheets, taking your data, make a histogram and show that they have that bell-shaped curve. If the sample sizes are above 30, we're going to assume the distributions are close-ish to normal, but also the sample size is big enough, it'll be okay. We have some calculations in the next 3 slides. Standard error there. Test statistic is here, using our sample standard deviations, our sample mean, population mean, and the sample size, and the degrees of freedom. So we used to have to take all this data and actually manually calculate each of these and then look up our answer in the back of the textbook. There'd be a huge table, and but there's no need for that anymore because this is very easy to plug all of this into a calculator that will just look up those values for us, and then we have that look up that in the back of the book or on their table that they have, and then they give us the p-value. So it's really handy. So let's do an example. I'll show you how to use that calculator. All right. So the average amount of time boys and girls aged 7 to 11 spend playing sports each day is believed to be the same. Studies done and data is collected, resulting in this table. Each population has a normal distribution. All right, so pretty small sample size here. If the sample size is below 30, they told us it's a normal distribution, so we would need to prove that it's a normal distribution if they didn't tell us that. So sample size of 9 and 16. So the 9 girls, they spent 2 hours outside, or 2 hours just playing sports. The boys spent 3.2. It's a pretty big difference there. The sample standard deviation tells us how spread apart the data is. So 0.866 over here and 1 for the boys. So the question is there a difference in the average amount of time boys and girls aged 7 to 11 play sports each day and test at the 5%? So our null hypothesis here is assuming everything is the same. So we would say the average of the boys and the girls, they're equal to each other. And the the alternative hypothesis would be not equal to. So we're testing both ends of this. So this is a two-tailed test. Okay, so watch how slick this is. I'm going to well, first of all, I made a little sheet that has, see if it loads up, but it has all the calculators for each section here. Okay, that's not loading. Okay, well, I'll just show you this calculator and I'll show you that sheet on a future video. All right, so I just need to record my numbers. So sample size of 9 and 16. So go inside of here. It's a little slow this morning. 9 and 16. It's kind of nice as I update this, it shows me all of these visuals. Love this calculator. Average of 2 and 3.2. All right. Standard deviation of 0.866. And that standard deviation was 1. Just going to go back in and make sure I have that correct. Okay, it looks good for the boys. It looks good for the girls. Okay, so I have all the correct information in. Then down here, we get to pick what was our null hypothesis. And we wanted it to be equal to. So we want the difference. This D stands for the difference between the two. I want the difference between the two to be equal to 0. And we get to pick our confidence level. Maybe. Drag, drag, drag. Oh, computer's being slow. So 5% would be 95%, and 1% would be 99%. Okay, it's kind of being tricky here. Okay, but regardless of what that percent is, it's actually not really changing much here. So we can see our probability that this occurs is 0.0054. And so the chance of this happening is about half of 1%, 0.0054. So that's very rare to have happen. We wanted to test this at the 5% significance level. So this is a very rare event that's occurred. So the boys have spent more time playing sports compared to the girls. And we therefore, since sample 2, the average is greater, so we reject the null hypothesis and we accept the alternative that there is a difference between the boys and the girls playing sports. So that's our conclusion. We write up our summary, and that's that problem. So there is a difference. We've rejected. All right, let's do another one. This one, studies done by a community group in 2 neighboring colleges to determine which one graduates students with more math classes. College A has 11 graduates. Their average is 4 math classes with a standard deviation of 1.5 math classes. So each graduate over the course of 4 years, they've taken 4 math classes. So that's pretty good. College B, they average just 3.5 math classes, a little bit less with a standard deviation of 1. Okay, so the first one is a sample size of 11, an average of 4, and 1.5. So 11, 4, 1.5. 11, 4.5. And next one is 9, 3.5, and 1. Okay. And we wanted to test if college A has taken more math classes. So we want to see if college A compared to college B, if this one's bigger than this one. So that would be looking for the difference to be greater than 0. Oh, I think maybe less than 0. Let's see, difference. Okay, it must be taking this one minus this one. Okay. So sometimes you have to play around with these to make sure you get the correct null hypothesis. You can see when you do the two-tailed test, see how the probability is 0.39. Here the probability is 0.19. So you can see how those are doubling the 0.19, gets us really close to that 0.39. So here I notice that it's telling me to be on this lower end. So the difference between 2 and 1 is going to be 19%. So according to this data, 19% of the time this happens. And we wanted to test this at the 1% significance level. Well, 19% is not rare compared to 1%. It's not even rare compared to 5%. So if our p-value is ever above 0.05, we will never reject. So, and they tell us here, this calculator is really handy. So no significant difference. We